All right. It is 4 in Belgium, probably some other time where you guys are, but that means it is time for me to start this webinar of SCIA version 21.1. I will be talking to you guys about the composite column design according to the Eurocode. So if this was not the topic you were hoping for, feel free to stay and enjoy it anyway. All right. Before we get started on the composite column design in the brand new SCIA version, let's quickly recap the webinar and how it works. You guys are all muted during the webinar. This is because all of this gets recorded and will be put on YouTube afterwards. But if you have some questions, feel free to ask them in the questions box. I am alone today, so I will not be looking at the questions while I'm talking, because else I will forget what I'm talking about. But at the end of the webinar, I will go through all of your questions and try to get you guys a reply. So feel free to wait a little while after until I responded to your question. All right? And with all of that out of the way, let's get into the composite column design. So previously, we already had some composite column design available in our SCIA Engineer 32-bit version, but to be fair, it was not the most complete of modules. So with the migration to the 64-bit version, we have made the big decision to take this design in-house and fully develop this module by SCIA and revamp it and improve it for all of you guys to use. In this webinar, I will first give you some explanation about all of the checks that are in this new module and how they are working. And then in a later point, I will open SCIA Engineer and give you a live demo. Very brave of me. I hope everything goes well, but I think it will. And I will show you live in SCIA Engineer what the new model looks like and how you can use it. All right. So first thing first, the supported cross sections. Very simple. All of the composite column sections that we have available in SCIA Engineer can also be checked by our composite column design module. So this goes for fully encased, partially encased, and concrete filled composite columns, as you can see on this slide. Next thing that we will do before starting the Eurocode check is check if the column that we have is actually valid for this check. And so there are a few requirements of validity for the Eurocode composite column check to be used, mainly one on the steel grades that can be used, the concrete grades, that can be used, and steel contribution ratio, for example, that all have to be checked. In the output of SCIA Engineer, you will very quickly easily see this in this table, if all the statuses are okay or not, and if they're not okay, you see the reference to where in the codes this rule is prescribed. So very easily for you to find out why your composite column cannot be checked and how to adapt it. If our composite column is valid, we move on to the next step, which is not the check yet. And this is actually also a step that occurs whether or not you are running the check. And this is the calculation of the effective flexural stiffness, or in other words, the adapted E modulus for the long-term effects that are happening on our concrete side. Yeah, so this new effective modulus, this new stiffness of your column is actually calculated before you run the calculation, and it's taken with in the calculation of SCIA Engineer. So if you go to the deformation results menu, this will be accounting for the creep effects already in the deformations of your entire structure. So this is a good thing to know, but if you want to know how we obtained this specific value, you will find it in the output of the composite column design. And second thing to do before starting our composite column check is to see whether our design moment has to be increased, be it for second order effects or be it due to imperfections of our members not being built perfectly straight. Yeah, so this is the second step that will happen before starting the check. Now for composite column, the imperfections and second order effects are taken into account a little bit differently than our standard steel check, for example. So I will go a little bit more into a detailed explanation of this. But to start this explanation, we need to go to the compression verification for composite columns that are under pure compression. Because the new module actually supports two methods to go check columns that are under pure compression. One of them is the European buckling curve method, which is actually the similar one to the one we know from steel, where depending on your section, well, let me show you the next slide already. So you see it here, depending on your type of cross section, you get a type of buckling curve, and this will give you some imperfection factor. And with this factor, you calculate the reduction factor, and you apply this reduction factor to your normal resistance, normal force resistance to account for the buckling. So this is the European buckling curve way of handling buckling effects and checking them. So this is one way you can go about checking your composite column in SCIA Engineer. And the second way is by means of the interaction curve. The interaction curve is also automatically used if you don't have a column under pure compression. So if you don't have pure compression, or if you decide to not use the European buckling curve method, you will go, instead of in this first row, you will go into the second row of my little scheme here, and you will do a check with the interaction curve. Now, the first thing that will be checked is my alpha critical bigger or equal to 10? That means, do I need to account for second order effects? If I don't, so if alpha critical is bigger, then I will still calculate a modified bending moment that accounts for the imperfections in my structure. Actually, a little bit like we would have the reduction factor if we use the European buckling curve method. In this method, instead of using some imperfection factor, we are going to increase the bending moment. So despite having pure compression, we will now get an additional bending moment. And if we need to consider second order effects, we will also increase this additional bending moment with the effects from our second order, so our second order effects. Yeah, so we will increase the bending moment even more. And then, of course, now that we have both compression and bending moment, we will use some interaction curve, which I will show you later, to see if our section can resist both the compression and the bending moment at the same time. And for the normal force in itself, we will just do a section check that ignores additional buckling effects. All right. So if I'm pure compression, either I go for the simplified European buckling curve method, or I go for the interaction curve and I get an additional moment calculated because of imperfections. And if I have second order effects, that increases this additional bending moment, and then I check the interaction with the normal force and the bending moment. Okay. A slightly different story is when you already do a second order analysis, because there we will assume that the second order effects will come out of this forces resulting from your second order calculation. And then if you have poor compression, we will just do the section check. And if you have also a bending moment there, we will do the interaction check and the compression check both. All right, I hope this is clear. It's a bit complicated, but it's not that hard, I think. There's just two methods that you can choose for in case of pure compression, and in all other cases, you will do an interaction check. Okay, so that's the European buckling curve methods. Okay, so slight additional topic and something new that wasn't there before is some positive effect that we can have on the compression resistance due to the confinement of our concrete. So if our concrete is fully encased in a steel section, then it cannot expand freely, and this will lead to some additional resistance being present in your section. The Eurocode prescribes how to calculate this additional resistance, and it is built into SCIA Engineer. All the formulas are in our theoretical background if you're interested in the specific details on how it is calculated, but that would lead us too far in the webinar. Okay, that's for pure compression. Now, if we have compression and bending, we will automatically go for the interaction curve method, as I told you. What is this interaction curve? Well, actually, it's a curve representing all the maximal resistances possible in your section for a certain normal force value and a certain bending moment value. And you see that this has this slightly weird shape, and that's of course because the more concrete is in compression, the more it is helping us. So at one point, actually having the additional normal force will help us out before it will start getting too much for the concrete as well, right? In the Eurocode, actually, they provide just some simplified way to calculate this A, D, C, and B points on the curve, and then they will do some linear interpolation between those. But SCIA Engineer will actually calculate all of these resistances precisely, and what you get in SCIA Engineer is the full black line, and you see that it will offer us some extra capacity compared to what the Eurocode will tell us, thanks to this accurate calculation of all of the points on the curve. Okay, yeah, that's actually what I wanted to say here as well, but here you see the way the interaction curve is shown in SCIA Engineer, as well as the points that are referred to in the Eurocode if you want to check it with comparison to the Eurocode methods. And then once you have your interaction curve, you can calculate from this what, knowing what your design normal force is, you can find what your maximum resistant bending moment is, what your capacity is left for taking up bending moments, and then you can have a unity check for this combination of forces. Okay. The final check that we do, and that's rather new, is the longitudinal shear check. Sorry. So what are we checking here? Well, if you apply some normal force on your composite column, the steel, of course, will react differently to the concrete. They have a different E modulus, and so they will want to have different displacements, but they cannot because they are one entity. So somehow they should be passing on forces to each other, and this happens through the longitudinal shear on the surface between our steel and our concrete. For this, there is a specific check built in SCIA Engineer, which will first go on and check if simply the friction between our concrete and our steel is enough to transfer the forces between the steel and the concrete. And if this is not sufficient, you are able to introduce your own studs and your own stud placement. And in that case, he will check whether your studs are sufficient as well. All right. Okay. So that's it for all of the specific checks. All of these checks have been verified against all of the benchmarks that we could find online for composite column design. If you would like to investigate these benchmarks or use them to show that SCIA Engineer is doing a good job at this, you will find them on our help website. And with this and with some references from the pictures that I have been using in my presentation, I will now leave the PowerPoint and open up SCIA Engineer. All right, I hope everyone is still following. If there's anything, don't hesitate to type in a question, all right? Okay, so I have here a SCIA project in which I've just inputted a column of each possible composite column type that there is. And if you would want to check it, of course, you run your calculation as you normally do with the engineer. And then you can go to our composite service. And then you will find here the new icon for the composite column ULS design, right? But before I go into the design, let's go into the composite settings. This composite settings is shared with the composite beam design module that we already have. But if you don't need that one, you can simply make it tiny and open the ones for the composite column design, and you will find all of the settings. At first, we have some buckling default settings to automatically calculate buckling factors. These ones, I will imagine you know them from the steel design, so I will not go into detail about this. If you want to, you can surely find some details about this on our help page, or just ask me. And then let's go into the ones that are specific for composite column design. At first, of course, we have our creep coefficient that you can adapt, which is used to recalculate the E modulus. And then the second thing that we need to know to calculate the adapted E modulus for the analysis and for the long-term effects is to know which amount, which ratio of the normal force on your beam is a permanent normal force. And so here you can adapt this value for a correct calculation of your E modulus. Okay, on the member check side, I've talked to you about using this simplified method for European buckling curves. If you tick it, that means that if you have a column under pure compression, it will be checked according to the European buckling curves. If you want to always use the interaction curves, then you can just untick this box, and we will also always go for the interaction methods. All right. For the longitudinal shear check, we need to know the lever arm, so we can calculate how the bending moment is going to translate in shear forces on our sides. This is generally taken as 0.9, so doesn't need adapting. If you need shear connectors, because the longitudinal shear track doesn't comply with only the friction between both materials, then you can enter the design here as well as the type of connectors. And then finally, the entire last part goes about the reinforcement that you would use in your composite column. And it is entirely similar to what you would use in the concrete design. So it works exactly the same as the concrete design. If you would want to adapt these factors for one beam in particular, I will okay this and go to our composite column data, then you can select some column on which you want to change the data, and then you can adapt this. So let's say that this particular column needs a different shear connector design, then I can change this to set this manually and change the number of connectors per row, or change the type of shear connectors, etc. for this member in particular. So these are exactly the same settings as in the setup, but then you can apply them to only one element in your project. Okay, and then finally to our main showing. It's the actual ULS check. You've already seen most of it, but now let's watch it in action. So I will refresh it. It works just like any check in SCIA Engineer. You have the same drawing settings where you can choose whatever is displayed, the way it is displayed. You can have an interval between which you want to display your stuff. You have the warnings, you have settings for the output. It works exactly the same. I will not go into full detail about this. Instead, I will go into full detail about the check and the detailed output itself. So let us just select one column in particular, and let me open for you the detailed output with the tables and the formulas, which is the biggest output we can get. And then I will open for you the preview. All right. So for the people that know our steel design, this will look very similar to you. And for the people who knew the old composite column design, it will probably look slightly different. This is our detailed output. We start off with some slight info about the element we are looking at. We have a type E cross section, which is a circular hollow cross section, then filled with C2530 concrete, and our unity check is 0.6. We start off with the partial safety factors that have been used, the material strengths and properties that are used in this check, and of course also the forces that can be found on my column. The next thing we do is calculate the cross-sectional characteristics. So we will find out from the cross-section which part of the area is structural steel, which part is reinforcing steel, and which part of the section is concrete. And then we will calculate the inertia moments around the both axes of our columns. Okay, next up are the second order effects and member imperfections. And here you will also find the recalculation of our E modulus, like I said to you. It of course happened before the check because we have used it in a calculation, but if you want to check how the value was reached, you will find it in the detailed output, as well as normally you'll always find the reference to the Eurocode chapter prescribing this way of calculation. So this is our changed E modulus. Next up, we will calculate, like I said, the modified design bending moment to account for the imperfections on our member. So this is the calculation that is done according to the reference that you can find here. And in the end, we will find whatever is the value of additional bending moment we need to use. And here below, you find two notes that our alpha critical is bigger than 10, and therefore we don't need to account for second order effects. So we do have an additional bending moment because of the imperfections, but not because of second order effects. The final step before running into the check is checking whether our column is valid to be used with these Eurocode prescriptions. So we will check the steel grade, concrete grade, contribution ratio of the steel, the slenderness, the maximum longitudinal reinforcement. We see that all of their statuses are okay. And if you ask for the output with the formulas, you will also, for each topic, see the formulas used for the check. And with all of that done, we're almost halfway of the output, we can finally start actually checking this column. So in this case, you see that we are calculating the plastic compression resistance. And then in our check, we will compare the actual compression that's present with our compression resistance. And you see that it is not being reduced with the key factor like we would do if we were using the European buckling check. Sorry, I'm talking too much. It's getting hard. Let me take a sip of water. All right. So you see that this key reduction for buckling is not present because we are accounting for the buckling with the modified bending moment in this case. Okay, next up we have some transverse shear check. Yeah, there is nothing really spectacular about this. We have some shear area, the yield strength, and our partial safety factor, which gives us the design resistance. And then we can figure out some unity check. Same for the second direction. And then we get into the combined compression and bending check. You see here already the calculated points of our interaction curve, but you can also find in the output the full interaction curve. Okay. Then we will calculate what the plastic bending moment resistance is considering the present normal force in our structure. And then we can go for a unity check for the one side for my, and then we repeat this procedure for z. So we see the full possible resistant points for every combination of normal forces and bending moments, but then we know what our normal force that is present is, and we can find out what the design moment that goes with it, what its value is, and then we can execute the check and find a unity check for the bending moment in that direction. Of course, these two unity checks are for each bending moment in each direction separately. So we have to come on and combine those, which is done in the following unity check, again, with the references to the code where you can find the used formulas. And yeah, then we get some unity check and we know whether our column is valid or not. Okay, and that brings us to our last check, which is present here, which is the longitudinal shear check. So where we are going to see if the forces between our concrete and our steel can be transferred with studs or without studs, or how much studs do we need. For this, it's a specific calculation where we will calculate, actually first, there will be some length of the column that is needed to transfer, wait, let me show you the slide again. So you see there is a specific length needed to go from this one force in the center of our column to a force that's distributed evenly between the steel and the concrete. So this is what we will call our introduction length. So over this length, we give the time for this force to get distributed over the entire section. And then we get some area for the friction, some friction area, and then we can see what the shear stresses are on here, and we can go compare them with the shear resistance. And in this case, the shear stresses on our sides between the steel and the concrete are smaller than the resistance, and therefore the check applies, and we will not be needing studs to have our column pass the checks. If we need studs, then this check will change. There will be an extra part checking the studs and seeing if they comply and if they are sufficient. Okay, now let me adapt quickly this column, and did I? No, there is still some tiny horizontal forces here. Let me remove them so that I can create for you a column under. Yeah, there also is still a bending moment. I will delete that one. Yes, okay. So I will remove them just so I can show you the design for a column under pure compression. Okay. There we go. And let's go back to our ULS check and rerun it and open the preview. Okay, so in this case, in my composite settings, I have the simplified method for European buckling curves active. So you will see, bad timing, you will see that for the compression check, which is a bit further away. Yeah, this should be the one. No, next one. Okay, I'm sorry. There we go. You will see for the compression check this time that we have an imperfection factor, we have a reduction factor. So as I promised you this time, when looking at the, no, I need to go further. When looking at the unity check here, yeah, we have the reduction factor that's multiplied with our plastic resistance, which this time is going to account for our buckling effect, as opposed to having the additional bending moment. So that's the difference. And then you saw some extra chapter appear, which is concrete in filled tubes. This is the one I talked to you about the confinement having a positive effect on our concrete. So here we are able to account for this additional positive effect that the confined concrete has some additional resistance in compression, and we are taking this into account. Okay, that's it from the composite column design. Of course, you have also the option to show a brief output where you have a view of the overall unity check and then can see the values of each check in between and see which ones are designing and which ones are really not. And yeah, I did not show you how to introduce the reinforcements, but honestly, it is pretty straightforward. Let me maybe, I had the other column still selected, but for adding reinforcement, you can just use the add reinforcement command, select the element on which you want to put reinforcement. You can choose to edit this template as you wish, or you can choose to use whatever you have inputted in your composite member data or whatever you had in the composite settings, or use the template. Let's load what I had in the composite member data, and my reinforcement gets added and automatically is considered in the ULS check. So yeah, no black magic there, but then I have also shown you this part. Okay, so that's the brand new composite column design. I hope it pleases you and it looks good. If it does not, feel free to send your feedback through to me. It would be very welcome. And then I will leave you with some quick preview onto the next version by telling you that next SCIA version release, we will also add the composite column fire design, and you will be able to check your columns for fire as well. Okay, that's it from me. Thank you all for attending, and I hope to see you in some of the other webinars that we will give about version 21.1. And if not, maybe some other time in one of my webinars. Thank you all for attending.